Here we are, lesson 3. Today we're going to talk a little bit more about polar graphs. This lesson is just an extension of the 3 additional skills needed for students who have plans to continue into calculus. In pre-calc, we set the foundation for later courses by considering those needed skills. Namely, they are the domain restrictions for completing one cycle of a polar graph, finding where the R values are negative, and then finding the points of intersection of 2 polar graphs. So that's going to be our focus today. Now, to save time, I've pre-filled some of our tables. Let's consider, if we will, the function y equals 1 plus 2 sine x. That's just our regular coordinate plane graph right here, from 0 to 2 pi, and how that relationship plays with the polar graph of r equals 1 plus 2 sine theta. See, we have a limacon with an inner loop. There's going to be unique y values on this domain, and we want to complete the table that's on the handout and here on my second page. So like I said, to save time, I filled in the y values for each angle measurement. And I went from 0 to 2 pi. And you notice that from 7 pi over 6 to 11 pi over 6, those answers or those y values in between that interval are the negative r values here. And we want to see what happens in relationship to our graph. That's the limacon with the inner loop. So the x, y's in my table become theta and r for the polar graph, but when we graph those, we graph them as radius and then the angle measurement. And that's going to generate this polar curve with the inner loop. And it's interesting to note that the inner loop is formed by the negative r values that we saw on our table. Notice I said 7 pi over 6 to 11 pi over 6. And if you look at the graph carefully, here's 7 pi over 6, right here. And here's 11 pi over 6. And you see how they barely hug that inner loop there. So 11 pi over 6. And when we get into calculus and polar curves and in Calc BC, we have to know the angles where those kind of events occur when we want to find the area inside of those loops. So again, like I said, that's for a later course. But that's how those graphs are related, where the negative values are, those create that inner loop on the limacon. Now the second skill we talked about, or the first skill I mean, is the domain restrictions. So how long does it take to graph one revolution? So one thing you can do is think about the zeros of the function and the period of the function. So we know cosine the period is 2 pi, and if we solved that equation for where cosine is negative, I'm going to subtract 3 and divide by 3, then the general solution is going to be at pi and every 2 pi radians, where n is an integer. So solving for n equals 0, or n equals 1, or n equals 2, we know that it's going to take from 0 to 2 pi in order to graph this entire dimpled cardioid. So we have this cardioid. And let me pull up a calculator here for a minute so you can look at the behavior. So if you look here, if I graph 3 plus 3 cosine theta, you notice that the step function goes from 0 to 2 pi. And if we take a look at that graph, well, it got me out of there. hold on a minute, menu, 3, 5, 3 plus 3 cosine theta. So you can see that the whole graph, 0 to 2 pi, it completes that curve. Where if we go back and change the step function, and instead of going 0 to 2 pi, we only went 0 to 1 pi, you can discover that it only graphs half of the graph. So where those zeros occur help me to determine how much or how many radians we need in order to get the entire domain and the entire complete cycle of the curve. For sine of 5 theta, again, if I solve for the zeros, I'm looking for where the sine of 5 theta equals 0. So sine is 0 at 0 and at pi, but sine has 2 pi for a period. So 0 divided by 5 and pi divided by 5 plus 2 pi in our cycle divided by 5 gives me a starting point so I can see what it'll take to get one full complete revolution of that graph. So substituting in the first one 0 and then 0 plus 2/5 of a pi, 2/5 of a pi, solving that expression, we're going to find out that we're having 0 and 2/5 and 4/5. Then if we take the second term, the second set of zeros at pi over 5 plus 2 pi over 5n and solve for those zeros. When n is 0, our first 0 is 1/5 of a pi, and then 2/5 plus 1/5 is 3/5 of a pi, and then 2 is our n, so 4/5 plus 1/5 is 5/5 of a pi, which is just 1 pi. So it seems reasonable that we could get between these zeros and these zeros that there are 1, 2, 3, 4, 5 zeros, and this gets me back to the beginning if you follow that kind of logic. So it seems reasonable to say that we would be able to graph one complete revolution of this particular sine function between 0 radians and pi radians. And again, I want to test that out with our calculator. So following that same type of logic, on my graph we've got 4 times the sine of 5 theta and I want the, I'm in the wrong mode there. We want to be in polar mode. 4 times the sine of 5 theta, sine 5 theta, and I want to try my interval being not 2 pi, but I believe we can graph the entire function in pi radians. And it's a 5-petal rose curve, and it takes pi radians to graph that. So much for the domain. Now we have 4 more to practice with. This one, cosine. So thinking about the zeros of cosine, cosine of 4 theta is 0 at pi and every 2 pi radians. And then cosine is 0 at, not pi, at pi over 2. And at 3 pi over 2 plus 2 pi radians. And we want to divide each one of these by 4. So our first set of zeros would come from pi over 8 to pi over 2, but I'm going to keep that as 4 pi over 8. And then our second set of zeros would come from 3 pi over 8 and pi over 2. So these would be my two formulas that would track down all of our zeros. And if there's 8 petals, we've got to get through at least 8 zeros plus 1 more to get us back to the pole on our graph. So working on this set of zeros, we got pi over 8 and 5 pi over 8. And then if we have a 2 for an n, that's 8 and 1, that's 9 pi over 8. And had a 3, we got 12 and 1, that's 13 pi over 8. So we got 4 zeros there. And this one, we got 3 8s when n is 0. And then 4 plus 3 is 7 8s when n is 1. And then when n is 2, that's 11 pi over 8. And then when n is 3, that's 12 and 3. That's 15 pi over 8. When n is 4, that's 16. That would put us over 19 pi over 8. Here we have 16, and that's 17 pi over 8. So it seems reasonable that this one would take a full 2 pi revolutions in order to complete all 8 cycles of the curve. And for cosine, that's going to be 0 at pi over 2 and at 3 pi over 2 plus 2 pi n. So this one, I believe, if you look at the graph with me, just for a little different approach here, going for cosine theta. And notice that my interval is set from 0 to pi. We can clearly see that we get all the full circle in pi radians, or we complete the circular curve in one complete cycle in 360 degrees. So 2 more to go. Lemniscate is going to take us I'm sorry, I said something wrong on the last curve. Go back. We got one complete cycle, not in 360 degrees, but in 180 degrees, just in pi radians. So it started here and then went around one time. So 180 degrees, we were done with the curve. Where this one, it's going to take pi to get one loop and pi to get another loop. So it's going to take 2 pi to work through that. And then the same thing, we saw this in the first example. We had 1 plus 2 sine theta. If you go back to that table, you notice it took 2 pi radians to complete one cycle of the graph because we needed to get back to the origin 3 times in order to make that loop. We had to start here, had to go through the loop. There's a second time and had to go around a third time to complete the full revolution of the graph. And that's going to happen the same in this case here. So similar to the first example, it would take 2 pi radians for that domain. So you just have to kind of play around, think about the zeros, look at the graph, and if you wanted to plot points, you could literally take and make a table, which is time consuming. And I'm trying to avoid that approach as much as I can to find which way the graph goes to begin with when the angle is 0 and where it goes secondly and how that curve happens. So the third skill we want to look at, and again, I filled in the table, pre-filled that in ahead of time to save time. So let's look at the table back from example 1 again and find the range of the positive angle values on the domain for where the R value is negative. So these positive angle values had negative R values in this interval from 5 pi over 4 to 7 pi over 4. And we wanted to know where the R values were negative, and I did that by taking 1 plus 2 sine theta and knowing where sine of theta was negative 1/2, and that happened at 7 pi over 6 and 11 pi over 6. So modeling what we would do is we could test that domain by making a test strip and dividing up our test strip between 0 and 2 pi, because we knew it took 2 pi radians to graph the full cycle, and test our zeros at 7 pi over 6 and 11 pi over 6. So remember we said that the negative R values create the loop. That's what we were looking at. The negative R values. Maybe make a note of that. Are what create that inner loop. Okay, so if we test the domain here with this test strip, and you test a number between 0 and 7 pi over 6, so let's say we tested pi over 2. So putting in a pi over 2 in our formula, 1 plus 2 sine of pi over 2, that's 1. So 2 times 1 is 2, plus 1 is 3, so we're positive. And that told me also that at pi over 2, our graph has a point at 3. If we test a number between 7 pi over 6 and 11 pi over 6, so let's say we did for, 7, so 3 pi over 2. So that's going to be 1 plus 2 times negative 1. So 1 minus 2 is negative 1, and we have a negative value in there. So when we had 3 pi over 2, we had a negative 1. Oh, there we had that. And then if we tested a number between 11 pi over 6 and 2 pi, so that could be, you can get a positive value in there. Let's say we tested 11 pi over 6, that'd be tiny. So here's what's happening. We have, using the tricks from before, if you had 1 plus 2, you got 3, and it had to be up, 1, 2, 3. And 1 minus 2 would be negative 1, but because it's a sine curve and its axis of symmetry is the y-axis or the line pi over 2, we needed 1 up from here to be the inner loop. And then we needed this A value, 1 to the right and 1 to the left. So what happened was we had the inner loop gets formed, and then we come outside, around, down, and back. Okay? So that inner loop was created on these angle measurements, 5 pi over 4 to 7 pi over 4. And if you looked, that would be somewhere in here. Somewhere in here. Those were where it started and stopped, and then the blue part was created from this region in the domain and this region in the domain. Okay, but it took us 2 pi radians for the domain in order to make one complete cycle of that graph or that polar curve, the limacon with an inner loop. Now here's one that we can work several steps. Let's use the rectangular graph of 2 cosine x minus 1, and we're going to find the range of the positive x values on the domain for which the y value is negative. So this is telling me to go just graph, I'm calling it an auxiliary graph, the rectangular graph of 2 cosine x minus 1. So let's do that with our calculator. We want to clear that out, go back to the graph just in rectangular mode and graph 2 cosine x, so we need an x variable, minus 1. And we're going to look at that graph between 0 and 2 pi. So I'm at 10 right now. So we want to look at, do a little math here first. Where is 2 cosine x minus 1, 0? That's going to happen where cosine is a half, and cosine is a half at pi over 3 and 5 pi over 3. So I'm going to use my graph, that rectangular graph, to help me cheat a little bit by looking at the function. So pi over 3 and 5 pi over 3 are my zeros, because I know that the domain for this particular function is between 0 and 2 pi. And we want to test this by looking at the graph. So what happens between 0 and pi over 3? You see that the function is positive there. And then what happens? This is our 0. And then between pi over 3 and 5 pi over 3, it's negative. And then 5 pi over 3 to 2 pi, we're going to stop right here at 2 pi, is positive. So this is telling me where the loop is made. And state the domain. Well, we did that up here. So the domain for one complete cycle is going to be from 0 to 2 pi. And then we remember what's happening here. In the symmetry, well, let's first do the graph. So the graph is going to have, what was it? 2 cosine x minus 1. So we wanted to have it's going to centered on right. It's going to be 1, and then 2 plus 1 is 3. 1, 2, 3. And then 1 up and 1 down. So it's going to have the inner loop here. And then it's going to come around here and go around to complete that loop. So there's symmetry on the x-axis, or the polar axis. I'll put that in parentheses. We've got symmetry on the polar axis, and we could test r theta is going to be the same as the opposite of theta, and then sketch that polar curve, which we've done. So putting all of those things together, going back, we use the auxiliary graph to know where the inner loop was formed, and drew the sketch, knowing that this was negative 1 plus 2 cosine theta, in that format, where this is the A and this is the B, and it's a positive cosine, so it's centered on to the right, and 2 plus 1 and 2 negative 1 minus 2 and negative 1 plus 2 told us those key points, and the 1 up and down told us which way to go. Okay? And then our last couple of examples, we are looking at points of intersection. You can find those algebraically. So again, if we have 1 minus 2 cosine theta, and you have r equals 1. We know here's the graph of 1 minus 2 cosine theta, and r equals 1. We know that we have 2 cosine theta is 0, and dividing by 2, cosine is 0 when theta is 90 degrees and 270 degrees. And we want to look at where, let's see, we want this intersection and this intersection. So one of them, this one's going to be when r is 1 and theta is pi over 2. And then this one's called a common point. That's not a solution, because they're just, this one's going around and around this way, and this one's starting here and going this way. So we're going to make a little note about that. When 1 pi is known as a common point. That's not a solution. And then we need the calculator to find these. So giving that a go, I'm going to change our view window to be polar. So we have r equals 1, and we have 1 minus 2 cosine theta. And I'm going to change my window a little bit so it's easier to see. Nope. We want to have the window set, let's say, we got -4 to maybe 3. Take a look at that. Menu 3, 1. That's rough. I want to make it square. There, that's better. Okay, so we want the intersection. And we're going to analyze to get an intersection. Got that graph. So I think I'm just going to write it this way. We can figure out what the decimal is. So the second one would be r2 theta 2, and that would be 1 and 3 pi over 2. So I know that this one is 1.571, and then we need 3 pi over 2 as a decimal. So 3 pi divided by 2 is going to be the 4.712. So this one would be 1 and 4.712. Now, one thing I want to show you is what happens at pi. So R1 of pi is 1, and R2 of pi is 3. So this is why I said 1 pi is called a common point, because on the first function, R1, what was our R1 function? When R equals 1, when R equals 1, y is 1. So R1 of 1. But when R equals 1 minus 2 cosine theta, that was 4. Is that correct? Let's take a look. Yes. No, it was 3. I'm sorry. It was 3. Oh, I could have gotten that by looking at the graph. So the first R, this was my first R, R1 of 1 is 1, and R2 of 1 is 3. That's why this is a common point. This is a common point. It's not a solution. Where these were actually having the same value at pi over 2. So looking at R of pi, we get 1, and R2 of pi, we get 3, and then R1 of 90 degrees, which is pi over 2, we get 1. And on the cosine curve at pi over 2, you see how they're not a common point? That's a solution. So when the angle is 90 degrees, our y value or our radius is 1. And you could check that on the other angle too. When the angle is 3 pi over 2, both of the radii will be 1, which makes them a solution. That's different than a common point. The common point had, when you put in pi, you got 1, and when you put in pi, you got 3. So those are two different things, a common point and a solution. And then find the points of intersection of the graphs for r equals 3 sine theta. So we want to know where they intersect. We'll set the equations equal to each other. And then 2 sine theta is 1 when sine is a half. So theta is pi over 6, or 5 pi over 6. And again, we want to graph those and check the r theta and the second r theta. So let's go back to our calculator and graph these. Okay, so here we've got our graphs, and then in my graph window, I'm going to check what we got for our zeros. What was it? Pi over 6. So I want to check at pi over 6. We got 1.5 on the first graph. And at pi over 6, we need the same value, 1.5. So that's a solution. That tells me we have a solution. So at 1.5 and pi over 6, (1.5) is the radius, and 30 degrees is the angle on both of them. We'll jump over to degrees. And then at 5 pi over 6, we want to do the same thing. So on the first one, at 5 pi over 6, we have 1.5, and the second one needs to be the same if it's a solution. 5 pi over 6, and they are the same. So we have 1.5 for the radius and 5 pi over 6. Those are our solutions. These are solutions. Now, do we have any common points? So it looks like at 0, that might be a common point. Let's go check it out. So on the first curve, if the angle is 0, the value is 0. And on the second one, if the angle is 0, the value is 1. So these are not in agreement. For R1, this is R1, and this was R2. If the angle is 0, the value was 0. But on R2, if the angle was 0, the value was 1. That means they pass through the point. It's a common point to them, but they pass through there at different times, where these have the same values. That's the end of our lesson. See you next time.